Hello, welcome to Pluralsight and to this course on Linux Systems Programming. I'm Dr. Chris Brown and this module is called Processes and Pipes. And in this module we're going to talk about, processes and pipes. I'll begin by discussing processes. I'll spend some time talking about what they are conceptually. Then we'll have a look at three important system calls: fork, exec and wait, and see how they're used to build the standard process lifecycle. In the second part of the chapter, we'll have a look at perhaps the most classic inter-process communication mechanism in Linux, the pipe, and we'll be meeting both the anonymous and the named varieties. We have some interesting demonstrations for you, including an attempt at a command interpreter, a shell. Now, I want to start by trying to make clear the difference between a program and a process. A program is a list of instructions waiting to be executed. It's a relatively passive kind of thing. A process is a more active kind of thing. It's sometimes described as an instance of a program in execution. Suppose you ask me to take the lid off my computer and show me the programs. Well, that's quite tricky. I suppose conceptually at least I could point to the instructions stored in memory and on the disk and say those are the programs. But if you were peering inside my computer and you said, well, where are the processes? That's actually a more difficult question to answer because the process is a more abstract kind of thing. Let's have a look at a couple of attempts at a definition. Some people will say a process is an instance of a program in execution. Now, there may be many programs stored in the computer that aren't running. There is no process. On the other hand, there may be programs that are being executed multiple times. There are multiple instances, multiple processes. An example of that would be the Apache web server, which spawns multiple instances of the HTTP daemon process to service multiple clients efficiently. Now here's a rather more down-to-earth definition. A process holds the resources a program needs to execute. And here we're viewing the process more as a sort of container. So let's explore that idea in a little bit more detail. What is the context that a process carries around with it? Well, first of all, it has a process ID. This is a simple integer. It's unique across the system. No two processes have the same process ID. It runs with a given user identity, the numeric user ID of the person who's running it. And then separately, it carries what's called the effective user identity, which determines whose permissions you're carrying around. I'll look at that in more detail in the next lesson. It has a current directory. You're familiar with that concept from using the shell at the command line. It has a priority which controls how favoured it is to the scheduler. Now, you cannot directly get or set the priority of a process. It does have a thing called the nice value, which affects the priority computation, but I don't intend to go into that here, and I'm certainly not going to talk about the operation of the process scheduler. The process carries around with it an environment, that list of name equals value pairs that we looked at in the last lesson. It has open streams, file descriptors coming back from an open call, for example. And it has what we call signal dispositions. That will make more sense in lesson 7 when we talk about signals, but basically it means the process has some settings which control how it will process the signals of each type. And importantly, the process has a number of memory regions. Let's have a look at those in a little bit more detail. There are actually 4 of them. First of all, we have the code segment, which is sometimes called the text segment, and that holds the program's code, the actual instructions that make up the program. It's attached into the process read-only. A process cannot modify its own code. And if we have several processes running the same program, the same code, they will actually share the code segment. The data segment holds global and static variables. That's in terms of C language programming anyway. And it's divided into initialized and uninitialized pieces. The initialized pieces for variables that are declared with an initialization clause so that they're explicitly given a value. And ironically, the uninitialized piece is also initialized. It's initialized to 0 when the process starts up. The stack is a region that grows and shrinks as the program executes. It holds a function's local variables. When a function is called, a stack frame is allocated for that function to hold its local variables, and when the function is returns, that stack frame is deallocated. So space on the stack is always allocated on a last in, first out basis. And then finally we have an area called the heap, which is used to allocate dynamic data structures. Historically, there is a call called SBRK, a system call that's used to control the size of the heap. You're not really supposed to use it. You're supposed to use the standard storage allocation routines, malloc and free, to dynamically manage memory. By the way, please don't read too much into this diagram. I'm not suggesting that the memory regions are laid out in exactly the order I've shown within the address space, or that they're neatly contiguous as I've shown here. I'm just illustrating that there are 4 memory regions. Let me give you one final analogy to help explain what a process is. We might imagine that a program is like the script of a play. It's a list of instructions of what to say and do. Whereas a process is like an actor, the agent responsible for actually obeying the instructions. I'll come back to that analogy later in the lesson.